Now let us see kinetics of elimination and therapeutic drug monitoring. The knowledge of kinetics of elimination of a drug provides a basis for as well as serves to devise rational dose regimes and to modify them according to individual needs. There are three fundamental pharmacokinetic parameters: bioavailability F, volume of distributions Vd, and clearance Cl, which must be understood. The first two have already been considered in chapter 2. During drug elimination is the sum total of metabolic inactivation and excretion. As depicted in figure 2.1, the drug elimination only from the central compartment, that is blood, which is in equilibrium with peripheral compartment, includes the site of action. Depending upon the ability of the body to eliminate a drug, a certain fraction of the central compartment may be considered to be totally cleared of a drug in a given period of time to account for elimination over the period. Clearance. The clearance of a drug is the theoretical volume of the plasma from which the drug is completely removed in the unit time. Analogy: creatine clearance, figure 3.4. So, 10 microgram per ml of drug enters. Organs of drug elimination are kidney, liver, etc. 500 microgram per minute is filtered, and less than 10 microgram per ml goes back into the plasma. So the clearance is 500 microgram per minute by 10 microgram per ml, that is 50 ml per minute. It can be calculated. Clearance is equal to rate of elimination by C, where C is the plasma concentration. For majority of the drugs, the processes involved in the elimination are not saturated over the clinically obtained concentration. They follow first order kinetics. The rate of elimination is directly proportional to the drug concentration. Clearance remains constant, or a constant fraction of the drug present in the body is eliminated in unit time. It implies to majority of drugs which do not saturate the elimination processes, transporters, enzymes, blood flow, etc., over the therapeutic concentration range. However, if the dose is high enough, elimination pathway of all drugs will get saturated. So, in the illustration of the concept of drug clearance, a fraction of drug molecule present in the plasma are removed of each passage through the organ of elimination. In the case shown, it requires 50 ml of plasma to account for the amount of drug being eliminated every minute. Clearance is 50 ml per minute. However, few drugs normally saturate. Eliminating mechanism are hardly can be handled. Zero order kinetics. The rate of elimination remains constant irrespective of the drug concentration. Clearance decreases with increase in the concentration, or the constant amount of drug is eliminated in unit time. For example, ethyl alcohol. This is called as capacity limited elimination or Michael-Mentis elimination. The elimination of some drug approaches saturation over the therapeutic range. Kinetics changes from first order to zero order higher doses. As a result of plasma concentration increases disproportionately with increase in the dose, which is in the figure 3.6, as occur in case of phenytoin, tolbutamide, theophylline, and warfarin. Since the dose rate plasma concentration plot is this case is curved, it is called as non-linear elimination. So average CPSS versus dose rate. For first order reaction it is linear, and for zero order it is not linear. Relationship between dose rate and average steady state plasma concentration of the drug eliminated by first order and measurement zero order kinetics. Blood flow dependent elimination. For few drugs, the eliminating capacity of an organ of elimination, kidney and liver, far exceeds the amount of drug normally presented to it by blood circulation. The elimination of such a drug becomes blood flow dependent. These highly extracted drugs are almost completely eliminated in the single passage through the organ of elimination. Plasma half-life. The plasma half-life T-half of the drug is the time taken for its plasma concentration to be reduced to half of its original value. Taking the simplest case of a drug given in intravenous through which has the rapid one compartment distribution and first order elimination, a semi-log plasma concentration time plot as shown in figure 3.5 is obtained. The plot has two slopes. Initial rapidly declining alpha phase due to distribution, later less declined beta phase due to elimination. The two half-lives distribution T-half and elimination can be calculated from the two slopes. The elimination half-life derived from the beta slopes is simply called the half-life of the drug. Plasma concentration in milligram per ml and time in hour. Alpha, the IV drug distribution, and beta elimination. The semi-log plasma concentration time plot of a drug eliminated by first order kinetics after intravenous injection. Since the first order kinetics is an exponential process, mathematically the elimination T-half is equal to ln2 by k, where ln2 is the natural logarithm of 2 or 0.693 and k is the elimination rate constant of the drug, that is the fraction of the total amount of drug in the body which is removed per unit time. For example, if 2 gram of drug is presented in the body and 0.1 gram is eliminated every hour, then k equals to 0.1 by 2, that is 0.05 or 5% per hour. It is calculated by k equals to clearance by volume of distribution. Therefore, T-half equals to 0.693 multiplied by volume of distribution into Cl. As such, the half-life is derived parameter from two variables, volume of distribution and clearance, both of which may change independently. It therefore is not an exact index for drug elimination. Nevertheless, it is simple and useful guide to the sojourn of the drug in the body, that is, after one half-life, 50% drug is eliminated. After two half-life, 75%, that is 50 plus 25 drug is eliminated. After three half-life, 87.5%, that is 50 plus 25 plus 12.5 drug is eliminated. After four half-life, 93.75, that is 50 plus 25 plus 12.5 plus 6.25 drug is eliminated. Thus, nearly complete drug elimination occurs in 6 to 5 half-lives. For drug elimination by first order kinetics, T-half remains constant because Vd and Cl does not change with the dose. Zero order kinetics, T half gets prolonged with the increase in the dose because Cl progressively decreases as the dose is increased. In fact, the concept of T half is meaningless for such drugs because it is not a fixed value. Half-life of some representative drugs: aspirin 4 hours, penicillin G 30 minutes, doxycycline 20 hours, doxin 40 hours, digoxin 40 hours, digitoxin 7 days, phenobarbital 90 hours. Repeated drug administration. When a drug is replaced by relatively short intervals, it accumulates in the body until elimination balances input and a steady plasma concentration CPSS is attained. CPSS is equal to dose rate by clearance. From this equation, it is implied that doubling the dose rate would double the average CPSS and so on. Further, it is a therapeutic plasma concentration of the drug has been worked out and its clearance is known. The dose rate needed to achieve the target CPSS can be determined. Dose rate equals to target CPSS into clearance. After oral administration, often only a fraction F of the dose reaches the systemic circulation in the active form. In such a case, dose rate equals to target CPSS into clearance divided by F. The dose rate CPSS relation is linear only in case of drug elimination by first order kinetics. For drugs example phenytoin, which follows Michelman's kinetics, elimination change for first order to zero order kinetics over the therapeutic rate, increase in the dose beyond the saturation level cause an increase in CPSS, which is an out of proportion to the change in the dose rate. In their case, rate of drug elimination Vmax into C by Km plus C, where C is the plasma concentration of the drug, Vmax is the maximum rate of drug elimination, and Km is the plasma concentration at which elimination rate is half the maximum. Plateau principle. When the constant dose of a drug is repeated before the expiry of 4 half-life, it would achieve higher peak concentration because some remnant of the previous dose will be present in the body. This continues with every dose until progressively increasing rate of elimination, which increases with increase in concentration. Balance the amount of administration over dose interval. Subsequently, plasma concentration plateau and fluctuates about an average steady state level. This is known as plateau principle of drug accumulation. Steady state is reached in 4 to 5 half-lives unless dose interval is very much longer than T half. The amplitude of fluctuation in plasma concentration at a steady state depends on the dose interval relative to the T half, that is difference between the maximum and minimum levels, less if smaller doses are repeated more frequently. Dose rate remains constant. When the drug is administered orally, absorption takes some time. Average CPSS is approximately 1/3 of the way between the minimal and maximal levels of dose interval. Target level strategy. For drugs whose effects are not easily quantifiable and safe margin is not big. For example, anticonvulsants, antidepressants, lithium, antiarrhythmic, theophylline, some antimicrobial, etc. are those given to prevent an event. It is best to aim at achieving a certain plasma concentration which has been defined to be therapeutic in range. Such data are not available for most drugs of this type. Drugs with short T half up to 2 to 3 hours administered at conventional interval of 6 to 12 hours achieve a target level only intermittently and fluctuations in the plasma concentrations are marked. So plasma concentration and time, multiples of T half, maximum, average, minimum. Plateau principle of drug administration on a repeated oral dosing, the area of the two shaded portion is equal. Okay, this area is equal to this area. In case of many drugs, penicillin, ampicillin, chloramphenicol, erythromycin, propranolol, this however therapeutically acceptable. For drugs with longer T half, a dose is sufficient to attain target concentration after single administration. If repeated will accumulate according to the plateau principle and produce toxicity later on. On the other hand, if the dosing is such as to attain target level at steady state, the therapeutic effect will be delayed by about 4 half-life. This may be clinically unacceptable. Such drugs are often administered by initial loading and subsequent maintenance doses. Now, what is loading dose? It is either single or few quickly repeated doses given in the beginning to attain target concentration rapidly. It may be calculated as loading dose equals to target plasma concentration into volume of distribution by F. Thus, the loading dose is governed only by volume of distribution and not by clearance or T half. Now, what is maintenance dose? Maintenance dose is the one that is to be repeated at specified intervals after attainment of target steady plasma concentration, so as to maintain the same by balancing elimination. The maintenance is governed by clearance and bioavailability of the drug. It facilitates for measurement of the drug concentration are available. Attainment of target level in a patient can be verified subsequently and dose rate adjusted if required. The two-phase dosing as described above provides the rapid therapeutic effect with long-term safety. This is frequently applied to digoxin, chloroquine, long-acting sulfonamides, doxycycline, amiodarone, etc. However, if there is no urgency, maintenance dose can be given from the beginning. The concept of loading and maintenance dose is valid also for short T half drug and IV administration is critically ill patient. Example, esmolol, T half less than 10 minutes used for episodic arterial fibrillation is given as an intravenous bolus dose followed by slow IV infusion or intermittent fractional bolus dose. Monitoring of plasma concentration of the drug. Therapeutic drug monitoring. It is clear that from the above consideration that the CPSS of a drug attained in a given patient depends on its F, VD and CL in that patient. Because each of these parameters varies considerably among individuals, the actual CPSS in a patient may be 1/3 to 3 times that calculated on the basis of population data. Measurement of plasma drug concentration can be given an estimate of pharmacokinetic variable in that patient and the magnitude of deviation from the average patient so that appropriate adjustment in a dosage regime can be made. In case of the drug obeying first order kinetic, revised dose rate is equal to previous dose rate into target CPSS by measured CPSS. The therapeutic drug monitoring TDM is particularly useful in following situation. Drugs with low safety margin, for example digoxin, anticonvulsants, antiarrhythmic, theophylline, aminoglycoside, antibiotics, lithium tricyclic antidepressants. If individual variations are large, for example antidepressant lithium, Potentially toxic drugs are used in the presence of renal failure, for example, aminoglycoside antibiotics, vancomycin. In case of poisoning, paracetamol poisoning. In case of failure to respond without any apparent reason, for example, antimicrobial, to check the patient compliance, anti-epileptic drug, psychopharmacological agent. Selection of the correct interval between the drug administration and drawing of blood sample for TDM is critical and depends on the purpose. When the purpose is dose adjustment, in case of drugs which need to act continuously, relatively long acting drugs, it is prudent to measure trough steady state blood levels, that is just prior to the next dose, because this is governed by both VD and CL. On the other hand, for short acting drugs which achieve therapeutic level only intermittently, ampicillin gentamicin sampling is done in an immediate post absorptive phase, usually after 1 to 2 hours, to reflect the peak levels. In case of poisoning, blood for drug level estimation should be taken at the earliest to confirm the poisoning and to assess its seriousness. It should be repeated at intervals to estimate the drug clearance of the affected patient and the need to hasten elimination, for example by hemodialysis. By C, for checking compliance of the medication. Even random blood sampling can be informative. Monitoring of plasma concentration for no value for first drug whose response is easily measurable, antihypertensive, hypoglycemic, diuretic, oral anticoagulants, inhalational general anesthetic. 2. Drug activated in the body, for example levodopa, hit and run drugs whose effect lasts much longer than the drug itself, reserpine, MAO inhibitors, omeprazole. 4th, drugs with irreversible action, organophosphate anticholesterase, phenoxybenzamine. So that's all. Thank you.